The point of view today is going to be that we've pretty much done the hard work on decomposing periodic operators with respect to the Fourier transform, and we're going to see some of the consequences and maybe I'll talk about some problems I'm working on, what I find is interesting, and maybe something that we can talk about during the next week or so. So you will remember that we were talking about periodic operators, and because of the fact that a periodic operator by definition is one that commutes with a certain discrete shift group, ZD, that means that we can decompose it in terms of eigenfunctions of the shift, which are exactly pseudo-periodic or quasi-periodic functions. And so we were able to take a periodic operator A and decompose it in this way. Now, so this, let me see. Let me go back to the quasi-momentum notation. Here's the quasi-momentum notation. Let's say I have an operator A that's periodic, and then I do the Fourier transform with respect to the discrete group action, the Bloch transform that I told you about. Then that operator can be written as a direct integral of operators that only depend on the quasi-momentum Z or the Bloch multiplier. And so let me show you some consequences then of this. One of the consequences of having a decomposable operator, say an operator A that can be written as an integral superposition of operators with respect to some measure, like on the torus, for periodic operators, is that the spectrum of the full operator can be obtained as the union of the spectra of all the sub-operators. And so this, in the case of a periodic operator, what that means is that the spectrum of that whole periodic operator, the Schrödinger operator or elliptic operator that we started with, can be obtained by taking the union over all the quasi-momentum of the spectrum of this A of K. So this is essentially the operator restricted to the quasi-momentum space. See, so it's a higher dimensional version of something that you know quite well in linear algebra, which is that you have commuting operators, and I can diagonalize one of them, and then I can restrict the other operator to each one of the eigenspaces. So what I'm doing is restricting the periodic operator to all of the eigenspaces of the shift, which are just the quasi-momentum spaces, you see? And then I look at the spectrum of the periodic operator on each one of those momentum spaces and find the spectrum there, and then take the union of all those spectrum. And then I get actually get the spectrum of the periodic operator. Now, it's true that spectrum, people study spectra of Schrödinger operators, and one of the things that they're interested in is what kind of spectrum is there. And if you know something from measure theory, it turns out that there are basically three kinds of spectrum. There's continuous, absolutely continuous spectrum. There's singular continuous spectrum, which is like a Cantor set, supported on Cantor type sets. And then there's point spectrum, which corresponds to eigenvalues, right? Now that's a much more delicate issue. For periodic operators, it always turns out that this union ends up giving you continuous bands of spectrum that give you absolutely continuous spectrum if the fundamental domain is compact. So what happens is that, you remember that this A here is actually restricted to a fundamental domain. I mentioned that last time at the end. You have this fundamental domain with quasi-periodic boundary conditions corresponding to that quasi-momentum. You find the eigenvalues of that, and you then take the union. So we have this question about what the eigenvalues are, or so what the spectrum of the operator for a particular quasi-momentum is, what the eigenvalues are. And I gave you an example back at the beginning with the graphene, the hexagonal type structure, a graph structure where we found out that a certain energy corresponded to a certain quasi-momentum. In other words, this energy was an eigenvalue of the operator simultaneously, so where the eigenfunction was simultaneously an eigenfunction of the shift with the quasi-momentum k. And so you got this relation between quasi-momentum and energy, right? And I showed you in that example that you can express that relation between quasi-momentum k and energy E by a function d that came out as a determinant of a certain matrix. And this happens with graph operators. And for other type of operators, it can be more complicated. But this is the central, this dispersion function, the zero set of this dispersion function was the central object in the title of this little mini series. Anyway, and so I want to remind you of this, that we're interested in this d function. I'm going to show you some of the consequences. All right, so first of all, the consequences of having this kind of a decomposition where the spectrum of the whole operator is the union of all this of spectra with respect to each quasi-momentum space, you get what's called a spectral band structure. And I want to show you without really any proofs just how this works. So for each, so you see this A here is an operator that depends on quasi-momentum. And this quasi-momentum K lives on the unit circle. Each component lives on the unit circle. And remember that the K was, so Z was equal to e to the ik. This was the flow K multiplier. This is the quasi-momentum. And this is a vector, right? Because they're D different directions of periodicity. So you can think of this A. So this A is typically can be proven to be an analytic function of the K or an analytic function of the Z. And so you have this analytic self-adjoint analytic family of operators. And there's a lot of theory on this, going back to Kato's big book and then and other treatments of this. And so what you find is that there are branches of this dispersion relation. In other words, you look at eigenfunctions of this AK and the eigenvalues and eigenfunctions of this A as a function of K. So as you change the K, you change the eigenvalues and you get what's called bands of eigenvalues. So imagine that for each K, I have a sequence of eigenvalues, EJK. Those are the eigenvalues. So EJK are the eigenvalues of AK, where J goes from 1 to infinity. So I have this infinite sequence of eigenvalues that depend on K as the operator varies with respect to K. And so there turns out typically to be an implicit, that these eigenvalues can be expressed in this implicit way through this dispersion function. So here's the quasi-momentum and here's the energy. And this energy depends on the quasi-momentum, but there's several, there are many eigenvalues, and each one of them depends on the K. And the theory of Kato and others tells you that if I have a multiplicity of one eigenvalue as of an analytically varying operator, then that eigenvalue varies analytically. And when several eigenvalues come together, then they split according to what we call a Puiseux series on a Riemann surface. So you have branches. You can have singularities where different branches come together. So this can be a somewhat complicated object, and the singularities are people are particularly interested in because they tell you certain interesting aspects of the time dynamics when you put everything together into the time dynamics. So let me show you how maybe you can use this idea to understand the operator better. Well, here's a picture that I pulled from Peter Kutschmann's review on elliptic periodic operators in 2016. And this is a picture of K1, K2 space. Say when I have 2 degrees of periodicity, I also have 2 quasi-momenta, K1 and K2. And for any particular value of K, the vector K, I have several eigenvalues. You see, so 3 of them are shown here. And as I vary the K, those eigenvalues vary. And these branches of the eigenvalue, multi-valued eigenvalue function are called the bands. the band functions. They're called the band functions for that operator. And so what you do is you want to look at what's the union over all of the k's. Find the union of all eigenvalues over all k's. And so you're really looking at the image of all of these bands together, the union of all those images. And it typically happens for periodic structures that there are certain energy intervals. So this is the energy axis right here. This is K1, K2. And there could be certain energy intervals like right here where two bands, one ends here and the other one starts above it. So there's sort of this gap in the energies that are actually obtained by taking the union over all the quasi-momenta. And that's called a gap in the spectrum. So there are bands and there are gaps. So this is the famous band gap type of structure that periodic operators give you. And it has been.
But in model 1T, right? They become increasingly unlike.
So yes, that's right. So there's something called the Bethe-Sommerfeld conjecture that's been proved in many cases up to now that says that in greater than one dimension, those gaps become more unlikely in such a way that there are only finitely many open gaps. And then eventually all of these different bands really overlap and give you a continuum at some point all the way up to infinity. So at some point you get all energies without any more gaps. And the number of gaps you have is something that people could be interested in. In one dimension, you take a homogeneous potential and you perturb it by an arbitrarily small periodic potential, then you will always get infinitely many gaps. That's something that can be proved relatively easily because it's one dimension and things simplify quite a bit. All right. Let me go back to the graphene example. Do you remember what that one where I had there were two vertices in the fundamental domain and three edges? So you take this structure and then you just repeat it like this periodically. And then I showed you how to compute the relation between quasi-momentum K. This should be a K1 and a K2 right there, and energy. So you reduce, actually what you do is you reduce the operator to a matrix because there are only two vertices in the fundamental domain. And so any pseudoperiodic function is actually determined by just two values in the fundamental domain. I showed you how to do that. And so you can reduce the operator at a particular quasi-momentum to just a matrix. And then you look at the eigenvalues of that matrix. That's how it works for graph operators. And so I just take the determinant of this thing and I get to this function of E and K1, K2 that I showed you as the example on the first day. And for graphene, there are actually two bands, J equaling 1 or 2, because it's a graph operator. It's bounded, it's a discrete graph operator. It's bounded, there are just two bands. But for a partial differential equation and for metric graphs or quantum graphs, there would be infinitely many bands, or at least infinitely many band functions that could overlap. So you wouldn't actually have the gaps after some point. Let's look at what we call a spectral resolution. So we've come to the point where we were able to decompose the periodic operator into all of these different eigenspaces of the shift, into the quasi-momentum spaces. Then we decomposed the operator on each one of those spaces into its eigenfunctions. So we've completely decomposed the original operator into all eigenvalues and eigenfunctions as finely as we possibly can. So what I'll do is say, let phi j of kx be an eigenstate corresponding to this eigenvalue for that particular quasi-momentum. Okay, so you take a quasi-momentum, you take the operator, you look at one of the eigenvalues ej, and then you take the eigenfunction corresponding to that, which is a quasi-periodic function. It's in the space of quasi-periodic functions for that particular quasi-momentum, and let this be the eigenstate corresponding to that. You would just find the kernel of this matrix with the appropriate E, as long as the determinant is equal to 0, then there's a null space. So that gives you these eigenstates. These are quasi-periodic with quasi-periodic parameter e to the ik, right? That's the phase factor when you shift. So let's say that these are the eigenstates. They are notice that these are not in L2. These are extended states, and we're particularly interested in the inverse Fourier transform, interested in the k's that are real. In other words, e to the ik is on the unit circle, because that's where those are the k's that you need for the inverse Fourier transform to recover the function, right? Just the unitary characters, if you remember that discussion. So first of all, let's say that yeah, I didn't mean to write this. I meant to write. This should be the eigen. This should be a fundamental domain. This is L2 of a fundamental domain. Or you can think about. Sorry about that. So suppose I'm looking at a function at the Bloch transform of a given. Oh no, this is what I meant to say. Sorry. So given the function L2 of x, I take the Bloch transform, as I showed you, and then I recover the f through the inverse Fourier transform. Now let's look at the f hat of kx. This, remember, is actually a quasi-periodic function with quasi-momentum k. And I can take this quasi-periodic function and I can expand it in these eigenfunctions of the Schrödinger operator restricted to that quasi-momentum space. And so this is the eigenfunction corresponding to that particular eigenvalue for that particular k. So the f hat of k is decomposed into these eigenfunctions. Okay, so this is looking at this decomposition of the operator over the whole torus. Look at a particular point on the torus. Look at the operator restricted to that quasi-momentum. Look at all of its eigenvalues and eigenfunctions, and write the component f hat for that particular quasi-momentum in terms of those eigenfunctions. And then you do this for every k. And then you want to take a superposition over all the k's. So what I'm showing you here is that, remember that we use these f hats to integrate over k to recover the f. But now I'm further decomposing the f hat into eigenfunctions of the operator, the A operator. See? And that's what this is. And then I do the inverse Fourier transform with the f hat further resolved into eigenfunctions of A. And so I get this. So look, this is a sum over the eigenfunctions over the different j's. So this is a sum here over energies, eigenvalues of A. And then it's an integral over all quasi-momentum. So this is the full spectral resolution of the original operator. Okay. So here's how I write the f. And I can think of these aj of k's as being all the parameters that I need to recover the f. So this is kind of like my full spectral transformation from the original f to a function of j and k. K is quasi-momentum, j indexes the energy. See? So this is my full transform. So I can think of a transformation from f to aj of k. So the aj of k completely encodes the f. And since these are eigenfunctions of the operator A, yeah, so I can, let me write this in a fancier way. So I'm integrating over all k's, and I'm also integrating over all j's. So I'm actually integrating over all quasi-momenta and all energies. So I'm really integrating over the whole Bloch variety. In other words, the zero set of the D function. So inside of KE space, so energy and momentum space, I have this zero set of the D of the dispersion function, right? The zero set of this dispersion function, D of KE, set that equal to 0, and I get this curve. This actually looks something like this. So I'm actually integrating over the whole curve. That's what I'm doing, because I integrate over K and then I sum over all of the E's. So I'm really integrating over the Bloch variety. And at every point on the Bloch variety, or the Bloch surface, I have a certain eigenfunction. And I can do this more abstractly and say, this is the Bloch variety for that particular A. It's just that zero set of D. And at every point, I can I have this eigenfunction that depends on the point, and it's a function of x, of course. See, this is a point, it's an abstract, you could say, point on the Bloch variety. And then I have this a depends on the point. See? So I have an a, so I just have this function of the point in the Bloch variety. I have to integrate over it to get the function. And it's this particular measure which actually depends on the k. So that's the measure. And guess what happens when you do a spectral resolution of an operator? Then you have completely diagonalized the operator. And that's what this shows here. Okay, so I can decompose the f in this way, where these coefficients represent the f. Well, now if I apply the a to the f, I have to apply the a to all of these eigenfunctions. Well, that just pulls out the energy E on the Bloch variety. So all I do is I multiply the a by the E. So what I've done is I've said this operator, this a, which was the Schrödinger operator or the Hamiltonian, often called the energy operator, is exactly written in such a way that I multiply the a by E. So it has become a multiplication by E. Literally. Does that make sense? So this is in momentum and energy space. And the function f is represented by some function a that depends on the point on this Bloch variety. It's a function on the Bloch variety that's representing the f. And then I multiply that function on the Bloch variety by the energy E. That is exactly applying the operator A. So this is a full spectral resolution of the Schrödinger operator. And it naturally sits inside of quasi-momentum and energy space.
So you would, for the initial data set, if you proceed program, so you would have you would represent the initial data
this way.
in this form.
You're talking about in time.
And then you would stick in into the I,
exactly.
T or something like that.
And that's exactly why I have this, because you mentioned something about resolvent and I wanted to come to that. Yeah, that's right. So if you want to do the time dynamics, and this F is your initial state, then, well, the time dynamics is given by the exponential of the A operator, e to the I A T. That's the operator that you have to apply to the F to get F at T. You see, because ddt, remember ddt of F is equal to IA F, right? And so at least formally, and you can make this precise using something called Stone's theorem, you can get F of T equals e to the IAT times the initial F. So this really means something, actually in terms of a Taylor series, or just by definition as what we call the group of unitary operators associated with that self-adjoint operator. So one-to-one correspondence. Something called Stone's theorem, if you want to look that up. And so yeah, what happens here now is that I could say, okay.
Sorry, but the Taylor series will go in theory.
Yeah.
The Taylor series will go if A is bounded. But bounded A.
Yeah. So the thing about the
spectral
that's right. Then you have to be much more careful, and you have to worry about the domain, and so on. Yeah. And then you find that whenever that semi-group has a derivative, gives exactly the domain, right, of the operator. This is very beautiful, right? It's like too beautiful. I don't know. Nothing can be too beautiful, I guess.
Yeah. So you could get the bounded. You could essentially get the bounded A.
Yeah, if you had a bounded A.
Especially prepared initially.
Yeah. Oh no, that is right. No, so it acts as if it were bounded on that initial data. Yes. Yeah. No, that's right. That's right. So let's see. So to get the time, so this is just what does the A do? This is representing the A, but there are many functions of A. So I can take any function of A. What does it mean to take a function of an operator? Well, I can declare this to mean that if I want F of, this is getting a little messy. If I want F of A, then I just put F of E, because the A is the E. I mean, the A is literally multiplication by E in this particular representation. So it would make sense that I take a function of E. And you know, if I have a diagonal matrix, I have a diagonal matrix, another one up to lambda n, and I take if I square this, I just square the eigenvalues. If I cube it, I cube the eigenvalues. And if I want a polynomial of this, I just apply the polynomial to the eigenvalues. And so then these would be the energies that I have there as a function of the point rather than a function of 1, 2, 3, n. So it becomes many points rather than and so now I can just say, okay, now I want to take the sign of a matrix. If I want the sign of this, I just do sine of lambda 1 and the sine of lambda n. So I can do any function of this matrix by applying it to the eigenvalue once I have diagonalized. So that's what it means to take a function of, say, a self-adjoint operator. Go to a spectral representation and apply that to the spectral value here. And so one of the things you can do is say, well, I'm interested in the time dynamics, so I can look at e to the I at times f. This tells me how the initial data f evolves in time according to that Schrodinger equation. Well, this is a function of a. It's an exponential function of the operator a. So this, what I'm writing here, is literally true. You write integral over the Bloch variety of e to the I, e of p, t, a of p, b, etc. So I just, in place of this e, I just put this function of e to the I, e. E to the IA becomes e to the IE. And if I want the resolvent, if I want to look at, say, say e minus lambda inverse, that's the resolvent. And this is what Kirill wrote down a little bit earlier today. He had a spectral resolution. Well, what I would want to put here in place of the e of p, I would replace this with 1 over e minus lambda, or z. Or z. Yeah, you see, you just, that, because the resolvent is a function of the operator. And what's nice is that this operator, which is acting formally as if it were just a number, can actually be replaced by a number e. You see? Take the resolvent of that. You just take the lambdas and replace them by 1 over lambda minus z, all the way down the diagonal. It's exactly what I'm doing. It's just a continuum version of that. Okay. Now there's something called density. Yes. Yeah. Yes, it is. Oh.
And separately, we also have its own functional calculus for self-adjoint. So how does that?
Okay, so this A is self-adjoint, let's say,
Yeah.
and these E's are real. This is they coincide exactly. This is a spectral resolution. This is so you can write down. Yeah, I could show you a little bit more carefully later, but this is a concrete spectral resolution. You know, Achilles Glatzman's book, for example, writes down spectral resolution for arbitrary self-adjoint operators in the Hilbert space, and it's abstract. You say there exists a resolution of the identity, right, etc. And then you can take that and multiply by lambda is the same as applying the function.
I think Yishin's question is about what change of variable, essentially.
So yeah, okay. So yeah, so what's happening here is there's literally a change of variable, or there's a unitary transformation from the original Hilbert space to this space to functions on the Bloch variety. Okay, and there it's actually multiplication, it's local. So and that actually gives you a concrete realization of the spectral resolution. Yeah, that's right. I mean,
it's much more than the
it's much more because it's concrete. It's like the Fourier transform gives you a concrete way to write down the spectral resolution of I times the derivative.
Yeah,
That's exactly, and this is now that kind of concrete spectral resolution. So what's the spectral resolution?
It's where you have the abstract one is where you integrate in respect to E.
Yeah, yeah, and this is E, and it's on the it's this P. Yeah, okay. So I could say No, that's right. I mean, I have to convert this to just E. That is correct. So I would have to look at cross sections of E. And I would have to integrate over all the Ks and get the spectral resolution. That's right. So this is even further resolved. In other words, you have a spectral resolution plus more. You've actually resolved each one of the fibers to the quasi-momenta. Yeah, okay, you're right. So this is more than that.
It's like a disintegration.
Yeah, disintegration of the measures. Yes, that's right. Kind of.
Instead of single measure, now you have like E and P.
Yeah. Now you have E and P or E and K. Yes, that's right. Yeah. Yeah. So the P operator is just instead of multiplying by E, you multiply by K. That's the momentum operator. Yeah. Yes. Okay, so then there's the density of states, and what you do, maybe I shouldn't spend too much time on this. What you do is you take this picture here and you pass over all energies, and you see how many Ks you get. Now you have to discretize the Ks in order to do this in a rigorous way to show what this really means. But suppose that I take a particular E here and I find a cross section overall, find all the quasi-momenta that correspond to that E. Well, let's say this was that cross section right here, and then I move the E a little bit and I get some more Ks. So what I really have to, the density of states, not the integrated density of states, but the density of states is essentially the integral over this Fermi variety at that particular energy of the inverse of the gradient of E.
Or, well.
Because it goes up.
Why is it different?
Oh, yeah, so this is fake because there are places where it might not be. Yeah, at singularities, you have to be careful. Yeah.
Singularities can be a problem.
Yes, singularities can be a problem. That's why I want to skip it. Okay, that's fine. This is morally correct. Okay, so is morally correct. Okay, here we have Wannier states. These are states that physicists are interested in. And so let me tell you essentially what they are. If you read the Wikipedia article on Wannier states, you get confused, or at least I do, but it's actually quite easy to explain what they are. So in order to get an arbitrary state F, I have to integrate something. I have to integrate certain multiples of all of the Bloch modes at every point on that whole Bloch variety. So they all play a part. So in other words, this picture here in energy momentum space is showing all the points where there's a Bloch state that plays a role in building every state. Okay, so an arbitrary state F has to be obtained by integrating some multiple of all of those Bloch states over the whole variety, all the way up to infinity. So the Wannier states, what they do is you take just one of the bands, often just the lowest band of energies, and you just integrate over that, and you look at all states that are obtained by integrating just over one of the bands. And then you ask one of the questions that people are interested in is whether those states that you get, whether you can choose the Bloch eigenfunctions in a nice enough way so that the function that you get out from there are localized, or exponentially localized. And the question has been addressed in a couple of papers, and the one that I think addressed it in most detail is by Kuchment in 2009. There was also a paper by Nensu in 1983. And it turns out that you can get exponentially localized Wannier states if you have time reversal symmetry and isolated, and that band is isolated, the lowest band is isolated from the others. The essential argument, basically the argument is a bit sophisticated, and you have to have, so at every point on this band, that this band's, right, let's see, this lowest one, say it's isolated from the one above it, and let's say it's smooth, let's pretend it's smooth. So you have a smooth band isolated from above, so it's really, it's a function on really the torus. So this is representing the torus, the K1, K2 space. And you have to make sure that you can actually construct a Bloch state at every point on that torus in such a way that you have what we call a smooth section. That means you can smoothly define it all the way around so that it's never equal to 0. And you can do that if that what they call the vector bundle of states at every point if it's trivial. And it turns out that happens. And so you have to be able to get a smooth section. And that happens when you have time reversal symmetry and the band is isolated that makes it smooth. And then you can get actually exponentially localized states. And so Kuchman showed this in 2009. Oh, what I mean is that it's exponentially decaying. So that these are localized at particular points in the space, and then they can be shifted around just by multiplying the eigenfunctions by an exponential in momentum space. You can shift them, and so you get these. So it's just short of getting, you can't get delta functions, but you can get exponentially decaying functions. So that's, yeah, and that's the best you can get. Yeah. Okay, here comes my favorite subject, and this is the reducibility or irreducibility of the Fermi and Bloch varieties. So we say that it's reducible if you can take that zero set that I showed you, the Bloch variety, and split it into two, if it's the union of two varieties. And one has to be a bit careful about this. And what it really means is that the dispersion function can be written as the product of two, d1 times the d2. All right. Now, if we're talking about a graph operator, then it turns out that from the example I showed you, you can see that we always got a polynomial in Z, or a Laurent polynomial where you can have negative exponents. So this is polynomial in Z. And it turns out that this is reducible in the algebraic sense. Let's say you fix the E and you're looking at reducibility of the Fermi surface, where you fix the energy and you just look at quasi-momentum space. So I fix the E, and let's say I'm looking at this factorization of a polynomial in Z into two polynomials. Well, how often can you take a polynomial in two variables or more and factor it? Pretty much never, right? The probability is 0. So that the coefficient, did you know that? If I take a polynomial in two variables, just write one down, you probably can't factor it. Well, if a human being wrote it down, you might be able to factor it because we tend to write down specific polynomials. So I'm not sure about that, but just the coefficients have to be very special. They have to satisfy certain relations in order for that to be factorable in two or more variables. And so this, on the face of it, seems to be a rare kind of event, reducibility, okay? Now, reducibility of the Bloch variety means that this is also polynomial in E for graphs. Now, when you go to partial differential equations, you have to look at analyticity in Z and a reduction into two analytic factors. So it becomes analytic geometry rather than algebraic geometry. But let's say we're thinking about the case of graphs in which this is a polynomial in the Z variable. So whenever you have this reducibility as polynomials, okay, then you have that Fermi surface is equal to the union of two of them. In other words, the zero set of D is the union of the zero set of D1 and the zero set of D2. So all these quasi-momentum energy pairs are coming from two different sources. One is the zero set of this polynomial. The other one's the zero set of this polynomial. Okay, and this happens when a polynomial is factorable, non-trivially. All right, and this can also happen for the Bloch variety. But I want to show you a consequence of irreducibility. This is maybe something I really want to get across, maybe the main consequence that I'm interested in sharing with you. There's a paper of Kuchman and Weinberg of 2006 that brought this to my attention. Now, I'm just going to give you a scenario and kind of develop an interesting situation for you. Suppose that I have a graph operator and it's periodic like the graphene one that I showed you in the example. Here's the operator and here's an energy, and I want to solve A minus EU equals F. And in all of Peter's lectures, he's actually solving something like this, right? I mean, there's a lot more to it, but he's solving an elliptic operator minus z applied to a function equals a forcing, and then he's doing homogenization. I'm just saying, suppose that if I just want to solve this, and I'll show you what I would like with the following properties. I want this f to have compact support. That means this forcing is just happening maybe at 1 point or 2 points. It's a certain number of points. I'm forcing it, and everywhere else, there's no forcing happening. Compact support forcing. I also want this, okay, so this is the forcing. This is, remember, we call this the response. You know, in other words, this is what you can impose. This is what actually happens. That's the response. U is the response to the forcing. It's the solution. So compact support forcing that you impose, and I want the response to be in L2. And so this is the weird thing. I want the response to be in L2. In particular, I actually want it to be exponentially decaying. But I also want the energy to be within the spectrum of the operator. So let me give you a little bit of physics thinking here. Okay, as far as the physicists are typically concerned, this would be the typical argument, or engineers, is that if I have this structure here that's periodic, and I have an energy that's inside of the spectrum, that means there exist Bloch waves at that energy that have momenta that allow it to propagate. So these Bloch waves are thought of as propagating waves in the direction of that quasi-momentum, and there are lots of quasi-momenta. So we're looking at an energy where there are lots of waves that allow propagation of energy out to infinity. We often call this radiation. And sometimes even in physics literature and engineering literature, they call these bands of spectrum, they call them radiation bands, because they're energy bands where radiation is possible. And then the gaps, no radiation is possible, and they call them stop bands because it gets stopped. Okay? So now I'm saying, let me suppose I want to force this structure at a particular point where that add an energy or frequency that is inside of the radiation spectrum. That's the third point there in the spectrum. So what you expect to happen, and what typically happens, is that will excite the Bloch waves that go out to infinity, and you will get radiation. But I want a response that doesn't radiate. That's weird. How can you get that? So I'm posing something that doesn't seem usually possible. I'm showing you how reducibility, I'm going to show you how reducibility of the Fermi surface will allow that and why. And so the basic idea is going to be that I have to force it in just the right way that I don't couple to the radiation modes. And how can I do that? The upshot, I just tell you right at the beginning, basic idea is going to be the Fermi surface will be reducible. There'll be two components. One of them has quasi-momenta that are on the units, are on the torus, and the other one does not. So one of them contributes spectrum, the other one doesn't. And I try to force it in such a way that I only excite the, so to speak, the component that doesn't contribute radiation. So let me see if I can explain this better now. Yeah, more mathematically.
So if I took the money F,
Yeah.
well,
Compact support.
So and just apply the result. Okay, so to
To resolve it doesn't even exist.
Slightly into the upper coupling.
Yeah.
Apply the result.
Yeah.
And pass the limit absorption.
You're probably going to get some radiation because it's in the spectrum.
Oh, okay.
Yeah, but now I want to, but Peter, what I'm doing, I'm trying to use a particular F in such a way when I take that limit, I access directions that don't have radiation. And so the interesting thing here now is that you can do this in kind of the easy way where you have a symmetry, even an odd symmetry. You force in the odd component, and where all the radiation is in the even component, then you kind of cheat your way through, maybe. But it turns out that reducibility of the Fermi surface allows you to do this also, and it does not always correspond to an operator decomposition. So there's this kind of algebraic decomposition, which is more general than the actual operator decomposition. which I find very fascinating. So look, if such U exists, then the physical way to say this, that a local forcing, that's the F, will produce a non-radiating response, that's the U in L2, at an energy within the radiation continuum. The radiation continuum is supposed to be what they call channels that channel energy away into radiation. And you're forcing it, and the energy should go into those channels. But you're trying to shield the forcing from the channels somehow of radiation. Okay, so you want degrees of freedom of the forcing that don't access those channels. See, that's the idea. Okay, so I'm going to show you basically how this works. In the quantum graph, or just the graph case, a hat of z, this is the restriction to the quasi-momentum z, is a polynomial, so Laurent polynomial. So it allows positive and negative powers if it has finite range. So I take the original problem a minus e, u equals f, and I go to the Fourier transform, the Bloch transform. So I take the Bloch transform of the f, Bloch transform of the response is what I'm looking for, and then I have decomposed the operator into all of its fibers. So this is the decomposition of the problem, and so I can solve this one z at a time, right? That's what decomposition does for you. Now, suppose that this d is irreducible. So what I'm saying is that this d is a function of z. So I'm fixing the energy, and now I'm looking at z, because now the quasi-momentum becomes the Fourier variable. Suppose it's irreducible as a function, the d is irreducible as a function of z. It cannot be factored into two polynomials, non-trivially. Now, if I solve the u, for the u, I get something like this. And this will not be an L2 if there's singularities on the chorus. Okay, so if this, and look, I want the E to be in the spectrum. So that means this does have singularities on the torus. There are values of Z on the torus. So why the torus, the compact torus? Because that's where I have to integrate over to do the inverse Fourier transform, right? So I don't want any singularities on the torus where I'm integrating over. But in order for E to be in the spectrum, the zero set of this, which is the Fermi variety, has to intersect the torus non-trivially. So I get singularities. So in order for this to be integrable and actually get something in L2, this F, in other words, the forcing, the Bloch transform of the forcing as a polynomial has to cancel all the zeros in the denominator. Okay, now there's a fundamental result of algebraic geometry for polynomials that have the property like the D does coming from a self-adjoint operator that says that in order to cancel the zeros of an irreducible polynomial on the torus, you have to identically cancel the whole polynomial symbolically. That's how strong it is. So the only way that you're going to cancel the zeros is to identically cancel the polynomial completely, so there's no denominator. So it becomes just a polynomial. The u becomes just a polynomial in z itself because that denominator goes away. It's not a rational function anymore. Now, this u hat then becomes a polynomial. Now, imagine taking the Bloch transform. When do you ever get a polynomial when you take this Bloch transform? It's a Laurent series with all the shifts. Well, that will be a polynomial if you only have finitely many non-zero shifts, which just means that the U has compact support. So the response will have compact support if I want it to be an L2 and the D is irreducible. That means I have a response that has compact support. And if you have any kind of principle of unique continuation, that can't happen. The whole thing has to be zero. Okay. So, but for graphs, this can happen. And that's kind of a weird thing about graphs. And that was the point of the Kuchman and Weinberg paper, was that for quantum graphs or discrete graph operators that are self-adjoint, it actually had to do with embedded eigenvalues, which I'll tell you about. But basically, a local forcing can only produce, within the spectrum, a local forcing can only produce a response that has compact support. And they can tell you just how big the compact support has to be. And for graphs that can happen because graphs are weird. Because you don't have a principle of unique continuation because of loop states and things like that. So for me, the upshot is if the D is irreducible, you can't solve this problem here unless except for compact responses, which in some sense I don't care about if I think of them as being non-physical as a model for my problem that should have unique continuation. Yeah. Anyway, so if it's reducible, what can you do? If it's reducible, let's say I reduce the D. So these are now polynomials. So I can now, if I want this to be an L2, and I want the E to be in the spectrum, that means only one of these has to vanish. In order for the E to be in this, only one of these has to vanish on the torus. So let's say that this one has zeros on the torus. In other words, the Fermi surface associated with this part of the D, this factor, intersects the torus non-trivially. That's where I get the spectrum from one of the components. But I range so that I'm in the gap for the other component, so that this one does not vanish on the torus. That's the setup. So I have to be in the gap of one and in the band of the other, coming from the other. Then I can arrange the forcings in such a way that they will exactly cancel this one only and not the other one. And so if I cancel this one, what I have left is a rational function and so the inverse Fourier transform of that will not be compactly supported. It would actually be exponentially decaying. It would be an L2. It's a rational function that's non-zero, and the torus will be non-zero in some vicinity of the torus because it's analytic. So that's how this goes. Now, the more interesting thing I think is this is kind of the first step toward creating embedded eigenvalues.
Sorry,
Yeah.
so this rational function.
Yeah.
Well, after you've canceled out,
Yeah.
F had D2, and you are losing the power, the maximal power. So the maximal power will be.
Yeah, there's stuff in here though.
Yeah, so
And there's
but
this.
That will be
Yeah.
so the power of Z in the denominator will be higher than the power of Z in the denominator. So that will decompose into a polynomial plus a proper rational function, and you'll have the same problem as before.
No, that's okay. No, it's okay. Let me see.
So
No,
it's
no. So
well,
so this is a
it's like-
matrix in general. We could even say, okay, let's even look at the case in which it's not a matrix and this is a scalar. Then I have a scalar divided by a polynomial. Yeah.
okay.
Yeah. Scalar polynomial divided by another polynomial.
Because
Yeah, typically there are matrix elements here, and this is actually a vector. So I'm being a little bit naive about this right now. I mean, you would have to take a vector, you'd have to multiply it by something that cancels this, and all components. Yeah. So it is a bit more complicated than what I'm actually showing you. But now what becomes a bit more complicated is suppose that I want to use this idea to create what we call embedded eigenvalues. Or so bound states at energies within the continuum. That means I have an eigenvalue, so an L2 eigenfunction of the operator, which means I have a bound state that's oscillating at a certain frequency, somehow trapped at a defect, at a frequency where there are radiation channels. And the typical wisdom would be that can't happen because the energy that's oscillating there would couple to the channels and radiate away. Okay, but what you try to do here is you say, suppose I have solved this problem with an E in the spectrum because I had a reducibility of the Fermi surface. Then what I can do is say, suppose I want to find, let's see if I can find a local potential B such that such that the F equals minus B times U. After I can solve this problem first, let's see if I can find a potential that now that I have the response and the forcing, I can set up the B so that F is equal to minus B times U. Make it a multiplication function. And basically I just have to make sure that where this is non-zero, this is also non-zero. there are things like that you have to check. But whenever I've tried, I've been able to do this, but I don't have a general theory of this right now. So once you do this, then you have A plus B minus E, U equals 0. And this U is in L2, the E is in the spectrum. And I got a embedded eigenvalue due to that defect. In other words, the defect is kind of together is conspiring with the bound state to act as the forcing, right? Yeah. So you can get embedded eigenvalues that way at local defects.
I'm sorry, can you go the other way around? So if you assume that you have an eigenvalue.
Yeah. Yeah. So if you have an embedded eigenvalue, you will
Can you go the other
act.
way around?
Yeah. Then you will definitely know that they would have to be reducible. It's the only way you can get it, because if you have embedded eigenvalue at a local,
So I was saying that.
then you automatically have this because you just write f is equal to that.
Precisely what I
Right,
thought.
that's right. That's right.
So basically,
Yeah.
can we assume therefore that those periodic situations, if you see the reducibility is equivalent to the presence of the attack.
Yeah. Unless they have compact support. Yes, that's right. That's right. That was the point of their paper. Yeah. And so so the idea of the paper was you can't have embedded eigenvalues unless they have compact support. Given that the Kuchman and Weinberg, 2006. But then, of course, given that the Fermi surface is irreducible, which it probably is. But then I started looking at some physics papers and I saw, look, they have embedded eigenvalues and things like this, a defect, and tried to figure out how that happens. And so that's actually a very interesting discussion. But so one of my efforts lately has been to try to figure out how you can get multi-layer structures that have a reducible Fermi surface and what you can do with that. Okay, so reducible Fermi surface, how can you get it? Let's just say that's an interesting problem already.
Is the periodic multi-layer structure,
Yeah.
is it like okay?
No,
what
not commensurate.
Okay, so
Yeah.
you've got an upper layer
Yeah.
and the 6 2 layers. Right?
Yeah.
There is a period for the upper layer,
Yeah.
and there is another period for the lower layer.
So with that's interesting. That also interests me right now. But let's say for this discussion, I'm looking purely at periodic multi-layers, such as AA stack graphing or AB stack
they're
graphing.
relatively periodic as well. So basically, the periods of the upper layer and the lower layer are
Commensurate. That's right. And even the same in all these.
The number of
Even-
tables of that, do you know?
Yes. Yes, I do. Yeah.
They
There's some
were
nice-
looking at the superconductivity.
Yes, I know.
Force to the subsubstances, right?
Yeah. Yeah, just. So and there's a lot of stuff about stacked graphing in the literature these days.
Because I basically picked the whole idea from Paul, so it's all good test. At some point.
It turns out that there's some nice theorems on when you can do AA stacked or AB stacked or just multiply stacked graphing. Graphing is special in many ways. One, because it's bipartite. One is because when you take out a vertex periodically, it splits it into finite pieces, right? So it stacked in graphene. It turns out there are certain restrictions on what the potentials can be on the different edges. But there are many ways in which you can do it so that the Fermi surface actually turns out to be reducible into the number of components that's equal to the number of layers. And that's the content of this paper and some other ones that I have recently. So for example, for AA stacked graphene, I have a picture here where I show that their Fermi surface is reducible into a blue factor and a red and a yellow factor. The blue factor gives you blue bands, and the yellow factor gives you yellow bands. And depending on what you do in the coupling, you can either preserve the Dirac points or you can disturb them. And a proof of when you can disturb them and when you have to preserve them is essentially in the work of Dr. Leitman Komich, but also Pfefferman and Weinstein. So let me see, it's 15:31, so I'm 1 minute over, and I have reached the very last page, and this is where I got tired. And this is where I wanted to say, well, suppose we go back to the magnetic operators. and it's this Harper model, and it turns out that it's not even periodic anymore, right? Or when I have two layers of graphene and they're twisted, then and maybe at some irrational angle, there's no period anymore. There's different ways to approach those. But one of the things I'm interested in is, does this idea of reducibility persist, even though there is no such thing as a Fermi surface? There should be something like that. And that looks to be doable in certain situations. Yeah. All right. That shall conclude my 3 lectures. Thank you for listening.
Thank you.